Hi everyone! Today we are going to use the equations of motion to define geostrophy, and then look at some examples of how we can use the geostrophic balance to calculate velocity in different layers of the ocean. So first I'm going to define geostrophy, and then the assumptions used to obtain the geostrophic balance. We'll start from the equations of motion. Once again, we have our advection terms and our Coriolis force on the left-hand side, and our pressure gradient and friction terms on the right. Geostrophic balance only applies to motion in two dimensions, namely the x and y direction. You'll see why in a second, but for simplicity, we'll leave out the vertical motion. Our assumptions for geostrophic motion are as follows. First, we have a steady flow, simply meaning that fluid properties are constant in time, so we can assume any partial derivative with respect to time is equal to 0. Our second assumption is that friction terms are small and can also be neglected. The final assumption for geostrophic motion is that our Rossby number is much less than 1, meaning that the effective rotation is much larger than our effective forces, so we can neglect the effective forces as well. Under these assumptions, we are left with our equations for geostrophic balance, which is defined as a balance between the Coriolis effect and the pressure gradient force. We can see now why there is only a balance in the x and y directions, because the Coriolis force does not act in the z direction. We can use this balance to solve for velocities in layers of the ocean. We will start with a very simple case, where we hold density constant throughout the water column, and therefore have only a one-layer scenario. Here's our box ocean. In this simple case, we have a tilt in the sea surface height so that the right-hand side is slightly higher than the left-hand side. We label this very small increase in sea surface height from 0 with the Greek letter eta. The depth of our ocean is negative h, and we'll refer to each side of the box as x sub a and x sub b, so our reference frame looks like this. Again, we have a constant density throughout in this scenario. Because the height of the free surface changes with x, we will have a horizontal pressure gradient force arising from the gradient in the weight of the overlaying water. So pressure will be greater at xb than at xa because the weight of the overlaying water is greater at xb than it is at xa. So first we need to solve for pressure at both xa and xb to calculate the pressure gradient across the length of x. In order to calculate pressure, we will recall the hydrostatic pressure equation from Lecture 2. This says that pressure at depth z is equal to the weight of the overlaying water at that depth. To calculate pressure at xa, we evaluate the integral from the surface to depth negative h. Solving the integral gives us the gravitational acceleration times the density rho times the depth z. Substituting in for the depths, we can solve for the pressure at xa is equal to the gravitational acceleration times density times the depth h. The pressure at xb can be calculated in a similar way. except this time we will evaluate the integral from the height of the free surface eta to depth negative h. Solving for pressure at xb, as we did above, gives us g rho eta plus g rho h. We can now solve for velocity by plugging our pressures at xa and xb into the geostrophic balance. The partial derivative of pressure with respect to x can be approximated as the change in pressure in the x direction over the distance in which this change happened, or the distance between xb and xa. Plugging in values for pressure at xb and pressure at xa, we can obtain our expression for velocity v, which again is the velocity in the y direction. Now, this expression probably doesn't mean much to you, but we can plug in numbers and solve for v to determine a typical value for geostrophic motion. Here we'll draw our same simple one-layered boxed ocean again. For simplicity, let's say our density rho is equal to 1,000 kilograms per meters cubed. The depth is 50 meters, and the distance between xb and xa is 50 kilometers. The height of our free surface, eta, is 5 centimeters. Plugging these values into our equation and assuming we are in the northern hemisphere to determine the sign of F gives us a velocity in the y direction of 0.1 meters per second, which is equal to 10 centimeters per second. This is the typical scale of geostrophic motion. It is important to note the sign of this value is positive, so the direction of the velocity is in the positive y direction, or into the board. This makes sense, right? Because if we think about the pressure gradient in the x direction, we have higher pressure at xb than at xa because there is more water at xb, and the weight of the overlaying water is higher or larger. The water will move from high pressure to low pressure, so water will move from xb to xa. The Coriolis force will deflect this water to the right since we are in the northern hemisphere, and the resulting velocity will be in the positive y direction, or again, into the board. Okay, now we are going to look at our second case. In this case, we have a two-layered ocean, and our density is constant within the layer but changes between layers. This case is baroclinic, meaning that velocity is not constant through the water column, or in other words, the velocity changes with depth. So like density, velocity will stay constant within the layer but will differ between layers. If we draw our box ocean again, we have a tilt in the free surface again, so sea surface is higher on the right. The depth of the ocean is negative h, and we'll again label our points xa and xb. This is a two-layered ocean, so let's say our layer runs from negative ha to negative hb. In the top layer, or layer 1, we'll call our density rho 1 and our velocity v1. Same with the bottom layer, rho 2 and velocity 2. In this case, we'll need to solve for the pressure gradient in both the top and the bottom layers. We'll start with the top layer. Pressure at A1, so pressure, or PA1, since we're solving for pressure on the left-hand side of the top layer. PA1 can be solved for by integrating from the surface to some depth within the top layer that's above HA. Let's just call it negative Z1. The depth of Z1 is arbitrary, again, as long as it's above HA, because it ends up canceling out of the equation, which you'll see in a few minutes. Okay, so we'll solve our integral for pressure at A in the top layer, like we did before, to arrive at the following solution. Pressure at B in the top layer can be solved for in a similar way, except this time we integrate between the height of the free surface eta and depth negative Z1. Now that we've derived at our solution, we can plug PA1 and PA2 into the geostrophic relationship again. Note that I'm going to use the density of layer 1 on the bottom of this equation. It doesn't really matter if you use rho 1 or rho 2 here, but for consistency, I will continue to use rho 1 for the remainder of the video. You can use either here because density changes so little in the ocean, especially between layers, that it makes so little difference on your final answer for velocity. So substituting into the geostrophic equation and solving for v1, we can simplify the equation down and notice that our answer is the same as our simple case. We know that the velocity in this layer is once again equal to 0.1 meters per second. Now we'll solve for pressure in the bottom layer, or layer 2. This is where it gets a bit more complicated, because the pressure in the bottom layer will be the sum of the weight of the water in the top layer and the bottom layer. So PA2 is equal to the integral from the bottom, negative h, to negative HA of the gravitational acceleration times the density of the bottom layer, with respect to depth z, plus the integral from negative HA to the surface 0 of the gravitational acceleration times the density of the top layer with respect to z. Solving the integral, we can arrive at an equation for the pressure at XA of the bottom layer. This process can be repeated to find the pressure at XB of the bottom layer. This time we are integrating from the bottom, negative h, to negative HB of the gravitational acceleration times the density of layer 2 with respect to z, plus the integral from negative hb to the height of the free surface eta of the gravitational acceleration times the density of layer 1. And I apologize for the little skip in my video right there. My camera stopped recording on me, so make sure you get the whole equation here. And I apologize, this is negative hb to eta, not ha to 0. Solving these integrals, we arrive at an equation for the pressure at xb of the bottom layer. We can substitute into the geostrophic relation to solve for velocity in the bottom layer. Note again, we continue to arbitrarily use rho 1 in the geostrophic relation because density changes by so little in the ocean, it won't impact our velocity calculations. To calculate the density gradient in the x direction, we subtract the pressure of the bottom layer at xa from the pressure of the bottom layer at xb, and divide by the distance between xa and xb. We are left with our equation for the velocity in the bottom layer. Again, we'll substitute in values to solve for velocity in the bottom layer. Substituting in these values, we obtain a velocity of negative 0.03 meters per second. As before, the velocity in the top layer is 0.1 meters per second, and we determined that this flow is into the paper. However, in the bottom layer, our velocity is in the negative direction, meaning that our flow is out of the page. Take a minute and reason to yourself why this makes sense. We see that velocity in the top layer is not equal to the velocity in the bottom layer. Velocity therefore changes with depth, and again, this is what we call baroclinic. Our last case is a special case, where our velocity is constant through the water column and does not change with depth. Note that this concept of barotropic motion is important to conceptually understand. However, this is theoretical, since obviously velocity basically always changes with depth. Okay, so in the barotropic case, we have a similar setup as before, with rho 1 in the top layer and rho 2 in the bottom. Except this time, our HA is deeper than HB, so our layers are tilted the opposite direction. If we solve for pressure and plug into the hydrostatic equation, we can solve for velocity in the top layer again, and we will see that it is once again the same as in the simple case. Feel free to prove this to yourself if needed. We will go through the same steps as in the baroclinic case to find the pressure at both points in the bottom layer. If you feel comfortable with the math, try to go through it yourself and see if your answer matches mine. Otherwise, follow along with me. Now I'm going to plug in values from before. This gets a little bit long and messy, so bear with me here, and I apologize for how messy it ends up. But anyways, we know that the velocity in the bottom layer must equal the velocity in the top layer, so we can set v2 equal to 0.1 and solve for hb and ha. Again, see if you can find an equation relating ha to hb. If not, follow along with me again. Okay, so we get that HA minus HB has to equal 45 meters. This makes sense since we expect HA to be deeper than HB. Okay, so there's your introduction to the geostrophic relation and baroclinic and barotropic motion. I know that this video was a lot of math, so hopefully you were able to follow along. But if not, again, I think the Khan Academy video is posted. But feel free to email me or swing by office hours on Tuesday if you have any additional questions. Thanks, guys. See you in class on Thursday.